Hey everyone, and welcome back to The Explainer. I am so pumped to be here with you today because we're looking at one of the absolute coolest topics in modern engineering and design, additive manufacturing. If you've ever wondered how the objects around us are actually brought to life, everything from the sleek casing of your smartphone to the insanely complex components inside a jet engine, you are in exactly the right place. Let's get right into it. So, I want to kick things off today with a pretty massive question. How do you manufacture the impossible? No, seriously, think about it for a second. How on earth do engineers build these crazy internal geometries, or those super intricate lattices, or just shapes that traditional cutting tools literally cannot reach? Well, to figure that out, let's look at a deceptively simple object, a standard 3D coffee cup. This perfectly highlights the severe limits of what we call subtractive machining. See, when you start with a solid block of material and just carve away what you don't need, you hit physical roadblocks fast. Take the deep cavity of a cup. Sometimes it's just too deep to machine accurately. And what about that undercut right below the rim? You literally cannot carve that out without incredibly complex, super expensive multi-axis machining. And trying to get perfectly sharp internal corners? Yeah, traditional tools just can't do it. So to see how we bypass those physical limits, here is our roadmap for today's explainer. First, traditional versus additive manufacturing. Second, the core additive principle. Third, we'll weigh the advantages and limitations. And finally, we'll wrap up with the common additive processes being used out in the industry right now. All right, part one, traditional versus additive manufacturing. The official ASTM definition of additive manufacturing is the process of joining materials to make objects from 3D model data, usually layer upon layer. I really want you to latch onto that phrase. Joining materials layer upon layer. It's like a direct pipeline from your brain to the real world. You take a digital CAD model, and the machine uses that data to build your final prototype by placing material only where it's needed, instead of worrying about where to cut it away. The contrast here is absolutely stark. Subtractive manufacturing begins with a big, solid chunk of stock material. Then a machinist or a computer-controlled cutter has to exhaustively carve away material until the shape is left. It's basically like sculpting a statue from marble. For complex parts, that is incredibly time-consuming and hugely expensive. Additive manufacturing, on the flip side, builds from absolute scratch. It literally generates the object layer by layer directly from the digital data. You use only the material you actually need, zero carving required. Moving right along to section 2, the core additive principle. Think of it like a giant 3D puzzle. In basically all commercial additive processes, a part gets fabricated by depositing layers contoured in a flat 2D plane, the XY plane. Then the third dimension, the Z direction, comes to life just by stacking these single layers on top of each other. But here's the catch. Because it's stacked, it's not a perfectly continuous curve. This creates a slight stair-stepping effect. If you want a perfectly smooth surface that looks exactly like your slick 3D model, you got to use extremely thin, fine layers to minimize those steps. Which brings us to section 3, advantages and limitations. Now, when we balance the pros and cons, the trade-offs become super clear. On the plus side, we're talking massively reduced lead times from product to market, huge reductions in waste, and my absolute favorite, the ability to create those impossible, highly complex shapes we talked about at the start. You can even combine multiple separate parts into a single print, a total game changer. But we have to be real about the limitations. High equipment and process costs are a major hurdle right now. Plus, the tech currently suffers from low speed, making it, frankly, pretty unsuitable for true mass production of millions of parts. Throw in some unexpected post-processing work and occasional inconsistencies in material properties compared to forged metals or injection-molded plastics, and you see it's not a magic bullet. Yet. Let's dive into our final section, common additive processes. While early methods like stereolithography used lasers to cure liquid resin, today we're going to focus heavily on powder and droplet methods. The big one is powder bed fusion, or PBF. Here's how the magic happens, step by step. First, a really thin layer of material, we're talking about 0.1 millimeters thick, basically a hair's breadth, is spread over a build platform. Next, a powerful laser blasts that layer, fusing the first cross-section of your digital model right into the powder. Then a roller sweeps in, spreading a fresh layer of powder right over the top. The laser fires again, and the process just repeats until the entire model is done. It's this continuous, mesmerizing cycle. Deposit, melt, lower the platform, and repeat. And what is absolutely fantastic about powder bed fusion is that the loose, unfused powder just stays there during the build. It literally acts as a built-in structural support for the part as it grows, so you don't have to print separate, wasteful support structures for overhangs. This whole category includes some heavy hitters you might have heard of, like selective laser sintering, direct metal laser sintering, and electron beam melting. Okay, next up is material jetting. Honestly, if you have a standard inkjet printer sitting on your desk right now, you already get the gist of this. A print head positions itself over the platform, but instead of ink, it shoots out tiny droplets of build material using thermal or piezoelectric tech. Those little droplets hit the surface and solidify to form your first layer. More layers get built up on top, and depending on the exact material, they either cool and harden naturally or, bam, they are instantly cured by a UV light. You can actually picture the print heads and the UV curing lamp actively sweeping back and forth across the platform. In this setup, you typically have two different vats of material, your main build material and a separate support material. Because unlike powder bed fusion, material jetting actually does require dedicated support material to be printed simultaneously to hold up those complex geometries. That extra material just gets washed or melted away later during post-processing. Our third major player is binder jetting. Now, a quick aside, unlike material extrusion where you squeeze hot plastic through a nozzle, binder jetting is a totally different beast because it bypasses melting completely. First, a roller spreads your powder over the platform. Then, an inkjet printhead zips over, but instead of depositing the actual build material or blasting it with a laser, it precisely drops a liquid binder adhesive directly onto the powder, only where the part needs to be solid. The platform lowers by a tiny fraction of a millimeter, and boom, this cycle repeats. So imagine a powder supply pushing material over, a roller leveling it out, and that inject head flying back and forth. As the platform slowly drops, your part is essentially being glued together layer by layer, buried inside that surrounding powder bed. And since there's no intense heat or crazy lasers during the printing phase, you completely avoid nightmares like thermal warping. Though, to be fair, these parts usually need some extra curing or infiltration later on to get their full mechanical strength. And that brings us to the end of our explainer. We've unpacked how additive manufacturing builds literally impossible shapes, layer by microscopic layer, from lasers melting powder to print heads jetting high-tech glue. But before we sign off, I want to leave you with a thought, really a challenge. We've seen that this tech is an absolute powerhouse for rapid prototyping and complex, low-volume parts. But looking at the current bottlenecks, how do you think the industry is going to evolve to overcome those massive speed and cost hurdles? How will it step up to truly conquer standardized global mass production? Definitely something to chew on. Thank you so much for hanging out with me on this deep dive into additive manufacturing, and I will catch you in the next explainer.